Welcome to Lecture 2 of the first week of the Geology of Nebraska. For this second mini lecture, we're going to be focusing on the geologic record and more so on how we actually determine the relative order of events that have occurred in the geologic past. We use something called the principle of uniformitarianism to do this. And so here we're just going to start by looking at how we observe modern processes and features in order to determine how past events might have occurred. So our first example here, we're going to be taking a look at sand dunes and how sand dune processes work today. So we're going to watch this short clip for a moment and observe some features that are happening on the Earth today. So first you can hear the sound of the sand blowing in the wind. What we can observe here is that on the left-hand side, we can see some sort of ripple marks, correct? So over there we have ripples. We can tell that sand or sediment is being moved, likely by the wind, since we're in a desert environment and you can see it blowing in the air. So here we have ripples, we have sediment blowing. And we can also observe that during this process, there's a shallower slope on the left-hand side of the video and a steeper slope on the right-hand side of the video. And as that sediment is being moved, it's moving from this shallow slope on the left-hand side to the steep slope on the right-hand side. Geologists use modern processes and observations of modern processes in order to infer how past processes may have worked. So here's an image of a rock outcrop. We can observe in this rock that there are many different layers and that these layers are angled. Now, remembering back to that video we just watched, we can also kind of compare these two processes together. We can notice that these layers are shallow on one slope, on the left-hand side, and that they're steeper on the other side of the slope on the right-hand side. Very similar to what we're seeing with that sand dune. We can also notice, for instance, that if we were to look up close to this rock, that it's made of sediment grains that are about sand-sized, also very similar to that dune process. So as a geologist, what we're looking to do is use these modern observations in order to kind of infer what kind of processes and events could have been happening in the past in order to make the rocks that we are seeing today. So again, for instance, in this picture, we might infer that this rock was formed from dune formation that eventually became cemented together to form the rock that we're seeing in this image. Uniformitarianism is going to be explored in much greater detail in next week's lectures. But for our purposes today, uniformitarianism means to make observations about modern processes in order to infer past events. Another way of stating this is that the present is actually the key to the past. But for now, this is all we're going to focus on, and this is to be continued next week. Today, we're mainly going to focus on what are known as Steno's principles of geology. This extremely handsome man on the right is Nicholas Steno. He was around in the 17th century, and he was a studier of natural history. So he really looked at a bunch of different natural history processes. One question that he was really focused on was, what are fossils, and how did those fossils actually get there? And on this path to answering this question, Nicholas Steno actually created some of the most fundamental principles that are still used in geology today. In order to do this, what he first observed are fossils in rocks. So he found features that looked very similar to what you're seeing on the image to the left that just popped up. We can observe that these are shells. They're different than the rock material that they're stuck in, and they have certain features that are very similar to features that we see today. such as clams that you might eat in a clam bake. So Nicholas Steno used modern inferences, modern observations of clams today to infer that those creatures must have been living in the past. They died and at some point were preserved in the geologic record. These observations eventually developed what are known as Steno's principles of geology, which are listed here. We have the principle of superposition, the principle of original horizontality, the principle of lateral continuity, the principle of cross-cutting relationships, and finally the principle of unconformities. So let's take a look at each of these in a little bit greater detail. The principle of superposition, very easily stated, simply means that the oldest layers are at the bottom while the youngest layers are at the top. So you can think of this as if you're building a layered cake. When you put the first layer of cake in the bottom, that is the layer that was deposited first, and thus it's the oldest layer. As you deposit the next layer of colored cake, this would be younger than the layer below it. And then finally, as you deposit the last layer of cake, that would be the youngest of the three. So again, for the principle of superposition, the oldest layers are at the bottom, while the youngest layers are at the top. The principle of original horizontality is also relatively easy to understand. If layers are originally deposited horizontally, as we saw in the previous slide, any folding or tilting or deformation of those layers had to have occurred after the deposition of those layers. So in other words, you need to have those layers there in order for them to be deformed. So we can infer that deposition occurred first, and then any deformation must have happened after. So that's a younger event. So we can visualize this here as well. So on the left are our horizontal layers. Again, our oldest are at the bottom, and our youngest would be at the top. And then after these layers have been deposited, they might be folded or tilted, but that folding or tilting must have happened after those layers were first deposited. The third principle is the principle of lateral continuity. And so this principle states that layers are laterally continuous over a given distance. So any removal or erosion of those layers must have happened after those layers were deposited. Now, some of these may seem very intuitive, but at first, when many people were studying geology, these principles weren't there. So when these layers are eroded, that erosion must have happened after those layers were deposited. So we can visualize this here with our layer cake. We've cut into that layer cake, and the layers are laterally continuous or the same on either side. And any of that removal must have happened after we deposited our layer cake. Similarly, we can look at geologic outcrops like this. So again, this is just another visualization, and we can see that the layers are the same on both sides, so that they were laterally continuous. A similar sort of principle here is the principle of cross-cutting relationships. So what this states is that any layer that cuts across another layer must have been deposited after the layer it cuts across. So again, on the left, we have our layer caked. Now let's imagine we inject some strawberry jelly into our layer cake. That strawberry jelly is younger than the layers that we deposited because it cuts across the layers that were first deposited there. This is also relevant in the geologic record here. So this is an image from the Grand Canyon, and we can see that the reddish layers are horizontal. Again, that's our superposition, our principle of original horizontality. But we have this black layer that's cutting across those red horizontal layers. So what that means is that that black layer that's cutting across those layers is younger than the red sediment. The final principle is the principle of unconformities. Now this is very important because the geologic record is extremely long. We have so much information there, but the geologic record is also very biased. There's a lot of missing information. erosional processes erase certain layers of rocks, and these are known as unconformities. So we can visualize this in the picture to the right. We begin with some mountains at the Earth's surface, but they're exposed to the elements and exposed to erosional processes like water erosion and wind erosion. And as those mountains are eroded away, it flattens the surface, creating this irregular erosional surface of topography. Now, say over time, that area is covered with water. We have sea level rise or we have a lake come in. More sediment is going to be deposited on that erosional surface. That erosional surface then is called an unconformity. We have three types of unconformities that we can have. There's a nonconformity, a disconformity, and an angular unconformity. These are explained in greater detail on the page in Top Hat, so be sure to take a look and read that information. Aside from Steno's original principles, there's one other really important principle that we have when determining the relative ages of events in geologic history. This is called faunal succession, or in other words, it's called biostratigraphy. This principle is based off of the fact that there are life forms that originate, they persist or live for a certain amount of time in geologic history, and then they disappear or go extinct. Thus, we can infer that certain organisms live during a distinct point in time, and we can use those ranges to infer the order of past events. So this is visualized on the right-hand side. We have a little gray fossil. This is called a trilobite. It's a relative of arthropods. They are extinct today, and they went extinct at a certain point in time in history. Above that, we have this reddish-brown color. It looks like a shell. This is called a brachiopod, and brachiopods, like trilobites, lived for a certain period of time and then went extinct. And then above that, we have other similar fossils that, in a similar fashion, lived for a certain amount of time and went extinct. So when we see those fossils, when we see this gray one, the trilobite, we know that it must have been alive during that point in time and that that rock layer that it was found in must have also been deposited during that time period. The same goes for our brachiopods up here and for the younger fossils at the top. So to summarize, a large portion of the geologic record requires determining the order in which past events occurred. We use these fundamental principles of geology to do this that Steno developed. This is called relative dating. It determines the order of events relative to one another. It does not give us absolute ages or absolute dates of those rocks, but it does allow us to come up with an order in which certain events happened. For this week, you're going to practice this for your first homework assignment. Again, all of our homework assignments are going to be found on Canvas this semester. So you will go to Canvas, and under the homework module, you'll open up the Homework 1 assignment or the Cross-Cutting Relationships assignment. This is due on Monday, 5/24/2021 at 11:59 p.m. If there are any questions on this homework assignment, please visit me at my office hours on Wednesday or Friday this week. And I hope that you enjoyed this first week of lectures. So, without further ado, we will finish up today's mini lecture, and you need to finish up reading today's page.